about what happens in sedimentation tanks. And we ended on this slide, and I'm realizing that this slide, it's just too much data. There's a graph with too much going on, but I tried to draw a line through like the important part. And the important part was that once the floc filter got up to the level where it was spilling over the floc weir, as soon as that happened, performance started to deteriorate. So high up on this graph is good performance. And you can see that it peaks right where the floc filter starts spilling over, and then it goes downhill. And the hypothesis is that at that point, and for the first time, we start dumping some of the beautiful blue flocs that are very porous and that were working to capture some of the red small particles that the flocculator failed to capture. And so we're wasting some of our wonderful floc filters before they've actually gotten to do their job for us. And I realize that you've not been thinking about drinking water treatment for 20 years or about how to make drinking water treatment work better, but that has been my passion for a long time. And so this gets me really excited, because this is like within the last year, we had this insight about what's limiting the performance of the floc filter. And see, before this, we knew that a floc filter was helpful and that performance improved when we had a floc filter in the bottom of our sedimentation tank. And we had this notion that somehow it's capturing the small particles that the flocculator is failing to flocculate, but we didn't know what the mechanism was. And now, because of looking at this graph and a few other things, we had this notion, oh, it's because the flocs are hanging out there and particles are actually going right into the floc and being captured by the particles that are already being held within the floc. So it's truly the floc acting as a filter. And see, what we needed is a hypothesis that explained why there's a finite capacity of a floc. Like, what about a floc wears out and becomes useless? And our previous hypothesis had been that, well, particles are attaching to the outside of the floc. And we couldn't figure out how that would work, because if particles are attaching to the outside, why can't they keep on attaching to the outside? Well, then the hypothesis was, well, maybe they were getting too big, and so there was too much shear on the outside. But there was another thing that was bothering us, and that is at the very bottom of the floc filter over here, there's this jet of water that's squirting out, and the velocity gradient at that jet is actually pretty high, and it's enough to break up the big flocs. So given that we're breaking up the big flocs right there, why isn't there infinite capacity of those big flocs to keep on then growing again and capturing more particles on the outside? So you see what we just learned? We previously thought that small particles were attaching on the outside, and we couldn't figure out how that would possibly make any sense, because then you should have infinite capacity, because when you get too big, you just break in half and you keep on growing. But now we think that's not what's happening. What's happening is you're capturing particles on the inside. And on the inside, once you're full, and there's no more space to put any more. Or as you capture particles on the inside, it's less porous, and so less water is actually sneaking up through that floc, and so that floc becomes useless because there's no water flowing through it anymore. So now we have a new hypothesis about what's limiting performance, and that gives us an opportunity. Because the whole point of doing the research and trying to figure out what's going on inside the floc filter is to see if we can figure out how to make it work better. So do you have any ideas? How would you make this flock filter work better? The blue guys are great, and the blue guys with red dots are a waste. They're already full. So what could you do? Anybody want to try? Be brave.
I know you mentioned yesterday about putting something like a filter in the bottom of it, so the more dense particles, like the full ones, go to the bottom, and they're exited out that way. But
Yeah.
I can't really think of any ones other than that right now.
Okay, so that's great. So this is this one idea that, wait, the one problem is that when we're wasting the flocks, we're wasting them over the top of this weir. And if you look at how did the blue guys get into the flock blanket? Remember that? Who can remember, sorry, the flock filter. How did the blue flocks, where did they come from? How did they get into the flock filter? Anybody remember?
Yeah, they were like an avalanche of the green ones that came up from the bottom and stuck to the plate settlers.
3 cheers. They were an avalanche of the green ones. So the green ones go up into the plate settlers. They avalanche down, and as they avalanche down, they grow in size. They turn into blue ones, bigger ones. So where are they coming in, and where are we wasting from? They're coming in right from the top, and we're wasting right from the top of the flock filter as well. So we are currently selectively removing the good guys. Do you see that? So if we can redesign how we take the flocks out of the flock filter when there's too many, we could perhaps improve that somewhat. That's one step that we'd like to take. And then I'd like to take an even more dramatic step. How else could I increase the concentration of blue guys? And more to the point, how could I take the ones that are wasted, the ones that are full of red dots, how could I take those and somehow turn them back into useful flocks? Any thoughts?
You could try to break them up or something, maybe.
That's exactly right. I've got to turn them like all the way back into at least green ones and maybe even red ones, and then send them through a flocculator again so that I can create more green ones. And that might sound like, what are you doing, Monroe? You're taking particles that had been perfectly removed, you're breaking them up again, and you're putting them back in the influent of the flocculator. But remember what the flocculator does. The flocculator can take a suspension of particles and it creates collisions, and it runs into problems when the space between the particles of the small particles is large. It has no problem at all making lots of collisions when the space between the particles is small. So if we dump a whole lot more dirt back into the flocculator, and it's dirt that already has coagulant on it, and we run that through the flocculator again, it's possible that it won't require the addition of much additional coagulant, and it'll very quickly grow up again into lots of green guys, which can go into the plate settlers, turn into lots of blue guys. And then all of a sudden, I've got a flock filter that has even more good blue guys in it. And so it'll work even better. That's a crazy dream. And if we're right, this could be pretty dramatic. And like, this is physics, right? We don't know yet what's going to happen. Like, it's possible that there's some reason why this won't work. That's why we're going to do the research. But you see why I get excited? Like it's possible that you could make a flock blanket or a flock filter that would capture, instead of maybe approaching 90% removal, maybe we would get 99% removal. And if you got 99% removal out of a flock filter, I think you could write home to your mother and explain that to her and be pretty proud. Okay, wow, I don't know if I was going to talk that much about this one slide, but I wanted you to see like these connections and why this matters, and how the fact that we for the first time we have some insight about what the actual physics is, that just opens up all the more doors. Okay. So I wanted to just like show the image of what's happening inside the plate settlers. So remember, inside the plate settlers, we have this aggregation of particles. So the flocks aggregate as they slide down the plate. So this is what that looks like. So an animation of that piece in more detail. Granted, I just said, did I say this? This is what this looks like? Like, I'm making this up, you know that, right? Like, I've never seen this. I'm imagining that this is what's happening. Okay, I just wanted to clarify. Although my students do like humor me and tell me that if you create an animation, then it's true. That PowerPoint has an automatic physics checker in it, and you can't actually animate anything if it's not physically real. I don't know. You can check that out later and see if that's true. Okay, so you saw it happen. You saw it happen on Monroe's slides. Bunch of particles went up, they slid down, they formed an avalanche, they aggregated into a larger particle. So that was good. That's how we get our blue guys. And this is cool. I think I didn't have this insight before putting together this set of notes, that I never knew how particles that are removed by a plate settler get to the bottom of a sedimentation tank. Did I talk about this on Tuesday? I've been talking about these ideas with a bunch of people lately because I'm pretty excited about them. So this is another cool insight. Everybody has plate settlers, not everybody, but most water treatment plants have plate settlers. And we go through the design for them is actually very simple. And you're like, yeah, we designed this plate settler, and the flocks get captured in the plate settler, and then they're removed from the bottom of the sedimentation tank. And they forget this one little piece, because in between the plate settler captures them and they're removed from the bottom of the sedimentation tank, you're assuming that these flocks have the ability to travel down through the sedimentation tank. And in most modern sedimentation tanks, the water is flowing up. And the reason that the flocks didn't stay in the bottom of the sedimentation tank initially is because they didn't settle fast enough to stay down. So how do they get to the bottom of the sedimentation tank ever? The only way they can ever get to the bottom of the sedimentation tank is if they gang up together and get a higher terminal velocity. So isn't that interesting? So that's what's happening inside these plate settlers. And it's been happening for decades, and nobody talked about it because we didn't really think about, well, what's going on that allows these particles to get back to the bottom of the sedimentation tank? Okay, and then there's this next point. As the big flocks fall from the plate settlers, they break if they're bigger than the size set by how strong they are, their bond strength and gravity. So that's the next piece. There's a messy equation that you didn't want to see, but just to say you can do the physics and come up with an equation that describes the maximum size that a flock can grow to. And so let's look at that. Do I do that one? Yes. So the next one is that these flocks have a maximum size. So let's look at that. So we have a flock that is falling out of the plate settlers. It's a bunch of green guys that have joined together to form a big, monstrous blue guy. It should actually be another color yet. It's bigger than a blue guy. And as it's falling, it's experiencing shear. And I think this is a little bit messy to think about, but think about a sphere, forget about the fact that it's a flock for a second. It's a sphere and there's water flowing around it. And that water is shearing, is applying a force of shear to that particle. And that's all rotating, like my hands are rotating around it. So there's this moment that's being applied, trying to actually tear the flock apart. Can you see that in your mind? That the flock at the bottom is experiencing tension and it's being pulled apart and try to roll it up. So all you have to do is provide enough shear so that the one bond that's holding this flock together gets broken. And remember, this is another key idea. We have the idea that these flocks form by rolling together I just realized that I made an assumption there that wasn't necessarily accurate. Okay, so let me step back. In the flocculator, we've learned that only similar sized particles can collide because of their boundary layers. They can't actually get close enough to touch. I don't know what happens in the plate settlers. In this avalanche, I don't know who all is combining. All I know is that there's a bunch of green guys up there and they're being rolled together and they form something that's quite a bit bigger. So the next part, you're going to have to critique a little bit. The assumption is that there's one, although you could change this assumption to say that it's a couple bonds that are actually holding the flock together at its weakest point. And so as the flock is slowly moving around, it's getting in tension at different places. And if the tension exceeds what the bonds can handle, pop, that thing opens up and we've got two flocks instead of one. And we've got to have another animation so that we can prove that this is what happens, right? So look, there it is. It happened. This flock was experiencing too much, this flock was experiencing too much shear, causing it to experience tension at the bottom, and it opens right up. And that sets the maximum size of a flock settling on planet Earth due to the force of gravity. You can actually, here I have the equation at the bottom again for what the diameter of that flock is. You could also solve for the terminal velocity of that flock. And you know what that means? It means that there's a maximum terminal velocity for flocks that you can get as a function of what the flock is made of, like how dense its core particle is. And that maximum terminal velocity means that if you design a sedimentation tank where the upflow velocity is faster than the terminal velocity of the biggest flocks, then nothing will be in your flock filter and nothing will be able to get out of the plate settlers and down to the bottom of the sedimentation tank. And that's an interesting failure mode that should be considered. It will happen under the worst conditions, and the worst conditions are cold temperatures when things settle slower, and flocks that are super low density, like organic flocks. Those are the ones that won't get to the bottom of your sedimentation tank if your upflow velocity is too high. I've got 5 minutes yet before you can give me a timeout. Okay, so let's talk about some laboratory results that we obtained. So you can actually see some of this, that it's not just an animation by Monroe, but actually some video, some real video that has been untampered. Okay, so this is some flock research that we did, and we were trying to figure out what's going on inside of our sedimentation tanks. And so what we did is we looked at our sedimentation tanks and we realized if we could take one little slice of a sedimentation tank from Honduras, that's half the width of a sedimentation tank. And if we could take that slice and bring it into the lab, so there it goes, 2,000 miles from Honduras to the lab. And then if we make it not 6 meters long like we do in Honduras, but we'd make it half an inch, sorry, switch to metric, 1.25 centimeters. And now we have this thin little sedimentation tank slice, and we can make it out of glass, and we can shine light through it, and we can actually see what's happening as Flocs move through that. So there it is. This system has a flocculator, and you should chuckle to yourself and say, Monroe, you didn't teach us how to design these flocculators. They're just a bunch of tubes wrapped around some cardboard, I don't know, pipes, tubes. And this is a laminar flow tube flocculator that works for really low flow rates. Doesn't make sense for municipal plants, but it works in the lab. And then there's the floc filter part of this unit, and there's the tube settlers, which are like plate settlers, except they're round instead of rectangular geometry. And there's no filter in this system. And now we run this, and let's see if this works. Okay, so this is video that was taken by my PhD student, now Dr. Casey Garland. And remember, she's shining light through it, and we're going to see what happens as a function of time. So here it goes. And hang on, let me pause this so I can talk a second. Okay, so on this graph, the blue line is the turbidity, or she's reported it in milligrams per liter coming out of the top of the tube settlers. So that's the clean settled water. The green line is a spot up here near the top of the floc blanket, above the floc blanket. It's supernatant coming off the top of the floc blanket. And this is great. Look at that. Look at that green line. It's like, I don't know, 300 or something, or 250. And it's constant the whole time. It never changes. Oh man, it's 248. I wonder why that never changes and why it's so high. And actually, Casey would jump in here and she would say, and it happens to be equal to the concentration coming out of the flocculator. Oh man, I'm going to stop right there and go back to this previous slide if I can. Hang on, I got to figure out PowerPoint tricks. So, and we're down to 1 minute. There's red and green coming out of the flocculator in the very bottom, this inlet manifold that's down here at the bottom. What happens to all the red and the green flocs? What happens to them as they go through the floc filter? Who gets left behind? Anyone? Who gets left behind in the floc filter of the red and green? I'll tell you because we're out of time. A couple of the red ones, they burrow into a blue one and are captured. But all the other ones go right through. And so the concentration up here where Casey was measuring it is all the green ones and still some of the red ones. And because the vast majority of the flocs, or the particles coming out of the flocculator, are green ones, they're already flocculated, the turbidity basically doesn't change. So all of the particles that came out of the flocculator are actually at the top of the floc filter too, minus a few red ones. And with that, I'm going to switch because I promised you I would. So we're going to stop this and we're going to switch to a really boring presentation that has no pictures and no animations. I'm so sorry. But you've been asking for something about feature script. And so I'm going to share just a little bit about feature script. And I dislike the fact that whenever you make a change in PowerPoint, it says, I'm going to make you configure all these tabs again. So now we'll do this one more time. And it is this one. Okay, so feature script and flocculator. I would encourage you to think about what actually has been missing that would help you as you work in feature script. So here are some strategies. to help you think as you're working through like the flocculator design. First thing is, for each step that I'm asking you to go through, make sure you understand what it is that you're trying to solve for in that step before you try to write any code. And one of the things that I'd like you to tease apart for me is the challenge feature script, or is the challenge figuring out how you would calculate this? Like, would it be equally challenging to calculate this with paper and pencil? Or would jotting something down in paper and pencil actually help give you clarity, and then you could do it more easily in feature script? But in any case, if you have a clear idea of what the thing is that you're trying to solve for, that will help you get to the next step. And it's more important to have the clear idea of what you're trying to solve for than it is to know which equation to use. Like, the first step is being clear about what it is you're trying to solve for. Yeah, and I said here, sometimes it helps to think about the values that you've already calculated. Like, what do you already know in this design? Now that you have some clarity about what it is that you're trying to solve in this next step, how could you use what you already know to figure out this next step? So that's a couple ideas. Another one is one step at a time. I think this is like so critical, and I know I get caught in this sometimes, and I've gotten better. I've learned as I've done more coding. As you code, check every step, and as soon as there's an error, don't keep on going, because it's only going to get worse. As soon as you get an error, track down that error and figure out what's going wrong. There's notices in feature notices of all the errors that are showing up. And if you keep on going, you're just going to get this accumulation of errors, and it's going to be confusing. And Izumi can vouch for this. You just get buried in errors. So what you want to do is, the first time you get an error, stop right there. And usually the very first line in the error report, and the first line that has the line number and position number of the error, that's what you want to click on, and it'll take you right to your feature script code to where the problem is. And I am keenly aware that the error messages are a little bit, they're terse, but if you start reading them, like they'll give you some nice insights. Like, they'll say things like, you tried to divide a number and undefined. That means that if you go look in the place where the error is, there was something that you were trying to divide. The first part, you had a number that was defined in a variable, and the second variable that you used was not yet defined in your code. So that means you have used the variable without defining it first. Another thing to think about is units. You're using units in all your calculations. And so as you're getting answers, make sure that the units are right, because if the units aren't right, you're going down the wrong path. So units are your friend. Make sure that each answer that you get actually makes sense. First, that the units are correct. And then the next step is use your engineering judgment. And I know that's not fair, because who has engineering judgment in college? You don't have much, but you're working on it, and you're beginning to develop some sense of what's possible. And so, like, at least if you were to calculate that the head loss in your flocculator was 1 kilometer, I would hope that your engineering judgment would turn on and you would say, wait, it can't be 1 kilometer, because I'd have to have a super deep tank, and that's not possible. Okay, so try to turn on that engineering judgment and try to think, like, does this answer make sense? At least ask the question, and as you do more of this, as you do more design work, that question will become easier to identify when you're out of the realm of possibility. Some ideas for if you've gone down this path and maybe you weren't paying attention, and so there were multiple errors, or maybe you did something and all of a sudden multiple errors show up and you're like, what in the world just happened? And there are ways that this happens. So what do you do? So one thing that you can do is move the rollback bar to be right below the first feature with an error. So this is in the Part Studio. Go into the Part Studio and move that roll bar back to the first place where there's an error, because it's in that first place where there's an error that you got to focus. Okay, that's first step. And then if there are still multiple errors, then you go into your feature script code and you can do kind of the same thing. You don't have a roll bar that you can move back in feature script, but you can comment out sections of code so that you're just looking at the code that's actually causing the problem. So you can comment out sections of code. And by the way, you can select a whole swath of code, and you can press Control/ and it will comment everything out. And when you want to bring it back, you just press Control/ again, and it'll bring it all back. So that's some ideas for when there's a whole bunch of errors and you're not sure which one to work on. You want to get it down to like the first error that's causing the problem. I will address this when I get to the code. Okay, so, and I want to give this idea. How can you check if you are all contributing equally to a design challenge? So let me stop this again. And now I want to go to feature script. I want to show you the solution. Good, it's still there. So I'm going to share another screen. And this is this. Okay, so now we're in my solution for this flocculator. This is what you're creating. And it is a big task. And so I'm happy that we're now giving you several more weeks to figure this out. So I asked the question of how do you tell if anyone else, what everyone on the team has been doing in this? So if I go to versions and history, I can open this up and I can look at each line here, and I wish they would show in detail like each line who did it, but maybe they do when more people are working, I can't tell. But anyway, I could look at each line, and I can't point on my screen, but look right next to my mouse, it says this was done by Monroe at 6:40 p.m. on February 2, okay? Every single change that was made in this document, I can see who did it. And it appears that Monroe is the only person who contributed anything to this design, which is because I created it. And so that's correct. So as your first exercise with your team, I would like you to, together with your team, roll down through your history in your document and see how has it been going. And you can reflect a little bit on that, because the goal is that all of you are contributing and you're all learning how this works. I recognize it's not going to come out 33, 33, 33 or 25, 25, 25%. But if there's a big gaping difference, then it's time to talk and figure out how can you do this better. What else could I tell you? What else would you like me to have told you about this design challenge? I have one other idea I could tell you for this design, and that is that the flocculator, this horizontal flocculator, is in some ways simpler than either of the other flocculators that we have already designed. And by the way, the reason that you can't find this design in the Aberclada set of designs is because we've never built this one or designed it. You're the first ones to design this flocculator, or I created the very first design of this for this design challenge. So that's why it's not completely documented yet. And the other thing to notice is that unlike both of the other flocculators, it's like there's only one channel. There's baffles in one row. In the horizontal vertical flocculator that we use most, the water goes up and down down one channel, and then goes through a little port, and then goes up and down, up and down, up and down in a second channel, or maybe even a third channel. But here, it's like there's only one channel. It's just baffle, 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 baffle in a straight line all the way down to the end. So that makes it a little bit easier to do this design because you don't have to figure out how wide individual channels need to be. And that's because like the human constraint doesn't show up here. These are big flocculators and there's no difficulty getting a human in between these baffles. So that ends up not being a significant constraint for this design. Whereas for the other designs, that was a critical part of the constraint and that made the design more complicated. Okay, I've talked a lot. Oh, one more thing. In case you haven't thought about what's happening in this feature, sorry, in the part studio. The part studio is literally like bringing in chunks of feature script code and executing them. And it's executing them from top to bottom. So this is a program over here on the left. And it executes starting at the top and going to the bottom. Here's that roll bar that I talked about. I can move that back to the beginning. Now the only thing that's executing is this one. This one is my code that is right here. So that's the only thing that's executing. Already at that point, all my variables are defined. So I can see the many variables that have already been created within my code, but my flocculator isn't showing up because I've rolled the roll bar back. Civil tank is also ultimately just a bunch of lines of code that are executing. And then we're just going down through this one at a time and executing them all. Who wants to ask a question that you're confused about and how this whole process works? Anyone?
I don't have a question per se, but I was just excited to realize that we're designing a horizontal flocculator. That must have been obvious, but this whole time I thought we were doing a horizontal, vertical, up and down, up and down. So I was visualizing this wrong the entire assignment.
Oh, and it's
us.
because I just label it HH and not horizontal,
Maybe,
horizontal.
yeah. I don't know. But we just had a big moment in our little group chat where we're like, oh my gosh, we're designing a different flocculator this whole time.
Oh, I'm sorry. Looks like there's more things I have to make clearer. And that's what I'm trying to do. Remember, you guys are like the first ones going through this. So as you are coming up with your questions, don't hesitate to share them because, man, I want to see those questions. With that, anybody else want to jump in with a question?
I have a really quick question. I hope this makes sense. I'm wondering why we have to do overrides for every assignment. Like, why can't we just rely on the code to spit out like everything that we need?
So the purpose of overrides is so that it's easy to change the design at the end. So for example, I can just go in here and I can edit this and I can say, I want to have a whole foot, 30 centimeters of height of the wall above the water. And I just made that change and that was fully implemented and changed. The overrides are actually like a key piece of how we're designing, how our Clutter Reach is designing things. And it allows us to have information from high up in the plant trickle down to lower level parts and have them all be controlled. I realize that that wouldn't be absolutely essential for like just designing the flocculator. Other questions? You can think of the overrides as where you kind of clearly put all the things that are potentially inputs to your design so that they're exposed. Okay, let's all jump in together, find your team, get a space to work at one of the whiteboards, and I will try to come around and you can also ping me with questions. I think you could chat me and I'll try to pay attention to that, although I know it's going to be chaotic, but spend this time working on the assignment. See you in Gather.